This laboratory focuses on RMS calculations and measurements because we will also be introduced to the spectrum analyzer this week, and the spectrum analyzer is a power versus frequency measuring device. And since power is always related to RMS, we need to look at RMS quantities. You will look at various waveforms from the signal generator: sine, square, ramp or triangle, pulse with given duty cycle, noise, and arbitrary waveform signals. Keep the frequency to be 1 kilohertz. If we return to the sine value, you can see that I have recording the frequency, the average value, the peak-to-peak value, and the RMS value. So you will need to record those 4 values for every waveform. We'll start out with a sine wave. We'll adjust the amplitude level or the offset level on the waveform. If we adjust the waveform up and down with offset, you'll see it change. Obviously, more offset, less offset. You may have to adjust your trigger, which is this control, until the orange trigger line is within the peak-to-peak amplitude of the waveform. The setup is straightforward. 1 cable between the generator and the ARB. Don't forget to turn on the output and just follow the instructions on the various waveforms. Once you have completed the RMS measurements on the various waveforms, I want you to return to a sine wave, but now we want the frequency to be much higher. We will select 1 megahertz for the frequency, and that is because the spectrum analyzer is a high frequency device. All right, so now we have our 1 megahertz signal. We'll auto scale to see it. All right, nothing special about this sine wave except it's operating at 1 megahertz. Now, in order to view the signal, we're going to use a BNCT. The BNCT allows us to look at the signal with the spectrum analyzer and the scope at the same time. So now we are ready to power on our spectrum analyzer. So simply push the button and it will go through its startup mode. This is very straightforward, just like a scope. It's checking internally that for its calibration points and the rest. Now the signal we are going to work with is a 1 megahertz signal. So in order to see that properly, we need to narrow the frequency range we are going to look at. So instead of looking 0 to 1.5 gigahertz, the stop frequency, we're going to look from 0 to 10 megahertz. So simply press stop frequency, type in 10 megahertz, and we see a new display. Now when we look at this display, you can see something on the left-hand side and then essentially some noise after that. Now this signal is actually the 0 frequency indicator, and this is very useful signal for us working with spectrum analyzers. So we'll connect up our spectrum analyzer. First we'll connect the signal on the analyzer, and then we will connect up to the scope signal. Now using the T connector, I want to monitor the signal on the scope when I connect, and if you notice when I connected, the signal on the scope reduced. So how come it reduced? Well, the signal generator has a 50 ohm output. Now the scope by itself has a 1 megohm input. We've checked that before, 1 megohm input. But the spectrum analyzer always has a 50 ohm input. So the input is 50 ohms. Since the generator is 50 ohms and the spectrum analyzer is 50 ohm, we see a reduction of the signal by 50%, or 2 to 1. So once you have the spectrum analyzer connected, you can no longer trust the readings on the ARB signal, which is what is generating. We trust the scope to give us the reading. So in this case, we're going to use the 201 millivolt signal. Now, on the spectrum analyzer, we said the display will be amplitude in dBm versus frequency. So we see our signal there. We actually see two signals. So if I take the signal away, we see the two signals, one at this point and one at this point, plus the zero indicator. So we only had one signal on our scope, so why are we seeing two signals on the spectrum analyzer? This signal is actually a bit of distortion. It's actually the third harmonic of the fundamental, or our sine wave, at 1 megahertz. And we'll talk more about that in great detail. But it's actually not nearly as significant in magnitude as it appears, because we are in the dB mode and every division is 10 dB. So 10, 20, 30, 40, that signal is nearly 50 dB below the original signal. Now, in order to take a reading on this signal, we're going to use the peak function. The peak function, when I press it, it will put a marker on the peak signal. And you can see that the marker says that that signal is 1 megahertz and minus 2.12 dBm. Now the calculation, if you go through the measurements or the calculated value, you'll see that the calculation for 201 millivolt signal is actually about minus 1.9 dBm. So there's our signal. If you want to look at the linear value, you simply go to amplitude, press linear, and then we see the peak signal will now be indicated at 1 megahertz and 175 millivolts RMS. Now that's slightly lower than the scope, which was indicating 2.01 millivolts RMS. That's our measurement setup for the introduction to the spectrum analyzer.